Well, hello guys, here we are again with another question from 2016. This one is question 5 and it's about momentum and the conservation of mechanical energy. We're going to solve this question, but before we solve the question, please don't forget to subscribe for the channel so you can get all the notifications and videos I post on regular basis. This question said a block of wood mass 1,595 kilograms is placed on the edge of a table 1,5 kilograms above the floor. The block is tagged by a bullet, mass 0,005 kg moving at an unknown horizontal speed. After the image of the bullet is immersed at the block which falls to the floor, the block strikes the floor with a speed of 5,6 meters per second. Ignore all type of friction. Okay, and there is the picture with most of the data that you have or you need here. Question 5.1 state the principle of conservation of mechanical energy in words. So we're going to start with question 5.1. Question 5.1 here at the bottom, 5.1 asks for the law of conservation of mechanical energy remains constant, and that is question 5.1. Question 5.2. Use the principle of conservation of mechanical energy to calculate the magnitude of the block with which the block leaves the table. And we have the final speed of the block right here with which it arrives to the ground. There's not friction on this side, so we are going to be working on this side of the motion there. Okay, so that is what we are going to start working here. So let's start with the principle of conservation of mechanical energy at this point. Question 5.2. 5.2. Now, what we're going to do, we're going to start saying that the change in mechanical energy total is equal to 0. You don't have to start from there if you want. Remember that this one will end up that the total mechanical energy initial is equal to the total mechanical energy final. And mechanical energy, guys, is the addition of kinetic energy plus potential energy. So we are going to substitute this one in there. Alright, so initial we have the total kinetic energy initial plus the total potential energy initial, and this is equal to total kinetic energy final plus total potential energy final. This is what we have here. And also remember the formulas for kinetic energy and potential energy. Now, those two formulas are given to you in the formula sheet. Here is the formula for kinetic energy. Here at this point is the formula for kinetic energy. And here up is the formula for potential energy. The symbol U is another symbol used, but it's the same formula. The symbol K is another symbol for kinetic energy. So we're going to take those two formulas and substitute in the equation 5 here at this point. The kinetic energy is equal to half mass multiplied by the speed square, and potential energy is mass acceleration due to gravity multiplied by height, and that is the two formulas we need to use here. Okay, now here we are going to substitute everything we have, but note the following. Here the bullet is inside the block when it left the table, so the mass here, mass of the block plus mass of the bullet, that is important to know that, because when the block left the table already had the bullet inside. So this one is going to be half. Let's write a little bit here because I want to edit so you can see it. Half the mass, but the mass is the mass of the block for the mass of the bullet. So it's going to be 1,595 plus 0,005. That is the mass. And the initial speed was 0, because note that the initial speed is the one we are looking for, the speed of which the block leave the table. That is what we are looking for. Okay, and now the same story here, guys, but this addition here I want to now sort it because I wanted just for you to see it, is equal to 1,6. So all this one here can be substituted by 1,6. 1,6, which we are going to do as from now on. And the final answer is 1,4 meters per second. So this is the speed with which the block leaves the table. That is question 5.2. Speed, calculate the speed. Use the principle of conservation to calculate the magnitude of the velocity with which the block leaves the table. State the principle of conservation of momentum in words. And guys, I want you to note something. That law is almost the same as the one here. In an isolated system, the total, instead of mechanical energy, you write linear momentum, remains constant. And that is the same, practically the same law as you see there. So let's write it anyway. Let's see if we have space. Let's go to a new page for that answer. And this question states that in an isolated system, the total linear momentum remains constant. You cannot forget here the word total, otherwise you are not going to get the math. Let's go to question 5.4. Now question 5.4 says calculate the magnitude of the velocity with which the bullet strikes the block. So now for this question we are going to be working with the other side of the motion, or the previous. Then we're going to work now with this part here, but we have the final velocity of the block when the bullet strikes the block, which was calculated already. So let's go to a new page to answer question 5.4. Question 5.4, all you have to do is to apply the law of conservation or principle of conservation of total momentum. We're going to start by saying that the total momentum is equal to 0. The change in total momentum is equal to 0 because it does not change. From there, we say that the total initial momentum is equal to the total final momentum. And then we have in two objects. We have the block and we have the bullet. So this one initial will be the initial momentum of the block plus the initial momentum of the bullet, and is equal to final momentum of the block plus the final momentum of the bullet. Okay, so this is what we have here. Now we are going to substitute the formula for momentum. The formula for momentum is given to you in the formulas, is here, and this one is the definition of momentum. So all you have to do is to read that one if they ask you to define momentum. Momentum is the product of mass and velocity of an object. Okay, so we are here, momentum is equal to the product of mass and velocity of an object, and we are going to substitute here. So we have mass of the block. Everything is for the block here. I'm not going to write here. Mass multiplied by the initial velocity of the block plus mass multiplied by the initial velocity of the bullet. You can use symbol 1 and 2 if you want. It's not a problem. Mass final velocity of the block plus mass final velocity of the bullet. We are looking at the initial velocity of the bullet. What is the velocity that the bullet had when it strike the block? And guys, the rest is substitution, which I am going to do real fast. Now note the following. Here at the back on this side here, the objects are moving together. Okay, they are moving together. I'm going to substitute everything. We have the final velocity there, but you can use a system if you want to there. Here, alternatively, remember you can do the following there, and you can say, for instance, This could be alternative if you want 1,4 bracket 1, let's write these numbers properly. 1,4 bracket 1,595 plus 0,005. You can write it like this if you want. It's the same, you will get exactly the same answer at the end. When you do this calculation, which is quite simple, you get that the initial velocity of the bullet is going to be equal to 448 meters per second. That is the answer we get for this question. In the question they ask for the magnitude of the velocity, so we don't have to give direction. Guys, this is the end of question 5 and the end of the video. We answered the whole question. The question, it was a good question to practice it. Since the beginning of the year you didn't practice this topic, but I hope it helped. Subscribe for the channel if you didn't, so you can get all the notification. Thank you for watching. I'll see you next time. Mr. G here.